Hello, and welcome to the 7th exciting chapter of Digital Design and Computer Architecture. In this chapter, the whole course is going to come together. So in the first part of the course, we began with 0 and 1 and worked our way up to logic design, to being able to design things like ALUs and memories and multiplexers. Then we jumped up to the high level. We looked at software and worked our way down to computer architecture, the native instructions run by the computer. And now we're going to meet in the middle to connect these two threads. In the topic of microarchitecture, we're going to look at how to put together hardware blocks to actually build a microprocessor. So we'll use all the components we developed in logic and connect them together in a way that we can run the machine language instructions of our RISC microprocessor. So as we look at a processor, one of the key issues will be how fast it is. So we'll talk about performance analysis. Then we'll look at 3 different possible implementations, 3 different microarchitectures of our RISC-V processor. The first one is a single cycle processor, where all the work takes place in one clock cycle. Because of this, the clock cycle has to be long enough to accommodate the most complicated instruction. Next, we'll look at a multi-cycle processor, where we break up the instruction into multiple simpler steps. And that will allow each step to run faster and also allow us to reuse some hardware. And we'll compare how that performance shapes up against a single cycle processor. Finally, we'll look at the pipelined processor. Earlier we'd talked about a pipelining example of doing laundry, and in the same way we can overlap the execution of various instructions to make them run a lot faster. So all modern processors where performance matters are pipelined. Finally, we'll survey some of the advanced microarchitecture techniques used in current processors. So as we said, microarchitecture is the way you implement the architecture in hardware. The architecture is the programmer's view of the machine, and the microarchitecture is the hardware designer's view. So we'll take our processor and divide it into a data path and a controller. The data path has the functional blocks that work on words of data, and the controller is going to make control signals to tell the data path to do the right things at the right time. As I mentioned, we'll look at 3 different implementations, 3 different microarchitectures of the same architecture. All of them will do the same thing. They'll all be RISC-V processors, but they'll have different trade-offs among how fast they work and how much hardware they take. So to measure speed, we look at the program execution time. The ultimate measure of how fast the processor is how long it takes to run a program of interest to us. And that execution time is the number of instructions in the program times the average number of clock cycles needed for each instruction times the number of seconds in a clock cycle. So let's define CPI to be the cycles per instruction. The clock period, also known as TC, is the number of seconds in a clock cycle. And sometimes we'll look at IPC, instructions per cycle. That's the reciprocal of the cycles per instruction. And our challenge is to satisfy some constraints of cost, power, and performance, or get the best performance we can under cost or power constraints. As we're building this processor, to keep things tractable, let's consider a subset of the most interesting RISC-V instructions. We'll look at the R-type instructions, add, subtract, and, or, and set less than. We'll look at the memory instructions, load word and store word, and the branch instruction, BEQ, and we'll build up a processor that handles these. Later on, we'll look at how to add other instructions, such as add I or jump and link. But once you get the fundamental ones, the rest are very similar. So the next important notion in microarchitecture is the architectural state. The architectural state determines everything that you need to know what a processor is doing. So if you took a processor and, well, in a science fiction movie, imagine taking somebody and freezing their brain and then 100 years later reimplanting it in a body and warming it back up, and the person's there again. We could do the same thing of freezing the brain of our processor. If we record the architectural state, then we could even turn off the power to the computer. Eventually we turn it back on, and if we restore the architectural state, the processor will keep going just as it was before. So in the RISC-V processor, the architectural state we need are the contents of the 32 registers, the value of the program counter, and the contents of the memory. If we restore those registers and restore what was in memory, and then put the program counter back where it was, the program will continue running just as it had. So any implementation of a RISC-V processor needs to have that architectural state. Here's the program counter. Here's the register file with 32 registers. And the memory we may break up into an instruction memory and a data memory to separately hold those two parts of the program and the data. So in the upcoming sections, we will connect this architectural state together with things like arithmetic logic units to do operations on the registers, and multiplexers to select the desired result, and put that together to build our data path, and then we'll make a controller that asserts the control signals to the data path at the right time.